Hello, welcome to week 5 of our R statistics workshop. This will be our final week, and I'm excited to talk to you today about linear models and matrix algebra that is found and utilized in cancer research. And we talked about like survival analysis last week. It was a very useful application of R and computational biology, right, to clinical analysis. And today we'll be talking about one of the most used concepts there is linear and logistic regression. And we also want to start this from the kind of the fundamental understanding of the underlying matrix algebra that goes into these calculations. So today we will be talking about different matrix algebra fundamentals. We'll be able to see the underlinings of them, how they're used to in the calculations of linear regression, and then we'll apply linear regression, log regression, and kind of evaluate the model performances, and then see how these can be used on our clinical data sets. So first, why matrix algebra and statistics? Well, when I started this whole course off, I talked about the importance of vectors, right? Vectors are the ability to use vectors and utilize these vectors in R allows for much more efficient computation, right? Much less memory usage, and it's really what R was made for, right? So by using, kind of in the same sense, by using matrix algebra under the engine, we can have more efficient computation of our regression coefficients in our linear logistic regression. We can understand our model geometry and the relationships better, and understand how we're really solving this from the bottom up. So let's get into it. So basic vectors and matrices. I'm sure you guys already know this, but we've been working with data frames for a while. So I wanted to just kind of remind you, vectors, C-bind any values. Matrices you build with the matrix instead of the data frame dot function, or you can also, C-bind several different vectors together if you'd like. But today we're working with just matrices, and it's kind of an obvious because we're just working with numbers only, right? So we have one data type. We're just going to be working with matrices. So what are a few matrix properties? Just very, very basic properties. As I want you to kind of start understanding how to play with matrices, because we're really going to be able to use this later when we talk about machine learning and deep learning. So here's just a very simple matrix, no big deal, some patients' genes. I just want to show you a couple simple operations. First, transposing. How do we transpose a matrix? Well, super simple. Just the T in the matrix, and it basically just flips it, right? Instead of gene A, B, C in the columns, now we're seeing those in the rows. So this is how we get our matrix there. How about a diagonal matrix? Well, if we want to create a diagonal matrices are extremely important and further our machine learning AI analysis. We'll often want to pull out and look at information from eigenvalues to covariances, things like that. We're going to be able to pull out these values. So if you want to build a matrix, a diagonal matrix, we use the DIAG, and just our numbers we want to put there. That makes my matrix here. But what if I want to grab these values instead? Well, simple. I use the diag function and the matrix this time. Instead of the numbers, I get the numbers back. So that's how we go both ways on that. What if I want to create an identity matrix? Super important thing to be used in computational biology mathematics. We just put the number we need because we already know they're all ones, right? So just how many ones do we want, right? So diag 4, we get our identity matrix there. Perfect. And then remember, obviously, if you want to look at the number of rows, columns, total elements, pretty easy to do that. We've already done that. Let's build upon this a little bit. What can we do with matrices, right? We can add and subtract them, right? So first, just how do we add and subtract a matrix? Well, first you have basic kind of an elemental addition and subtraction, right? So you basically just take, like you would think, each value, 2 plus 1 equals 3, right? 4 plus 2 equals 6. So really easy, right? It's a very easy way to get those calculations. It's just element-wise. You're basically just going to each element, adding them together, and they're staying in their same position. Same as subtraction. Go each way, stays the position. Okay, well, what about multiplication? Multiplication, much more important. Well, first we have element-wise multiplication. Once again, You just go back and forth, to your different things. 2 times 1, gives you 2. Really simple, right? So you just multiply across and just stay in your same spot. Really easy. All right, now let's get to some more interesting stuff, right? What's a scalar dot product? What if we want to multiply matrices together? I'm sure you've seen that little dot. So what does that little dot mean? And if you remember in your math courses, well, that's the scalar dot product or the inner product. And basically what's happening is at the scalar level, just take 2 vectors here, right? And there's 2 ways of doing this. So A dot, imagine that's A, that's B. A dot B, and in tidyverse, the dot matrix is like that. Instead of the pipe, we have the matrix symbol in the middle of 2 of the percentage signs. So that's A dot product B when you see that. So I'll get into this in a second, but really the easiest way of looking at this is just the dot product is just A1 B1 plus A2 B2. So A1 times B1 plus B1 times B2. So just elemental adding together each number. And an important relationship of this is if you think of these 2 vectors. Think of these 2 vectors, like that. I always have to do this backwards. So we have 2 vectors, right? They can either be the same direction. I'm like, how do I do this? The same direction, right? They can be 180 degrees. They can be 90 degrees, or they can be the same direction completely, right? So 90 degrees, same direction, right? So what's interesting is if you take the dot product of these 2 vectors, if they're perpendicular, right, then that's cosine of 90 degrees. So you see here, the dot product is also the magnitude of A times the magnitude of V, that's a real times cosine 90 degrees. So if it's perpendicular, cosine of 90 degrees equals 0. That means that A and B are orthogonal. They're perpendicular to each other. Now, in contrast, if it was 1, right, then if it was 0, then the cosine 0 is 1. They're equal to each other. All their information is passed along that same way, or that's how we get that relationship with the dot product. Very interesting relationship that's used for a lot of different things, including the underpinnings of linear and logistic regression. So that's how you would handle it if it was just a scalar, right? So that's great. And so you get a final value there, right? You're adding all of it up to a final value. But what if you have matrices? What do you do there? Well, you have a generalized dot product. And this is called vector matrix multiplication. So you can multiply matrices. This is where you multiply a vector times a matrix in these situations. It could also be matrix, but let's talk about vector time matrix here. And let's make 3 different things. Here we're going to make, if you think about y equals mx plus b, the definition of a line. Let's look at it in a little bit different, in a linear system instead. A little bit different, but it's tiny bit similar. It's similar enough where you can see it the same. But here we go, y, right, equals bx. Okay, let's just look at this kind of this way in the same kind of form, right? And let's make a y. Y is going to be your response vector, your answer, right, your result. X is going to be your design matrix. That's going to be your predictor values, right? And the beta is going to be your coefficients. That's going to be your coefficients, your slope on that graph, right? In a sense, as we move over to linear expression. Let's stay in kind of the world of linear systems right now, linear models, or linear systems, I mean, and let's look at what we created. So I just have a simple X matrix here, right? Where we have age, tumor size, we have 2 predictors. We've also put 1 in the intercept. And when you're doing linear regression, you'll always have a 1 in the intercept. And basically that is to bring in the B0 column, the B sub 0 variable. And if you don't have that, then basically here you're allowing the intercept to flow up and down. If you didn't have this, it would force it through 0. And you can imagine if the line was forced through 0, this way, right? If the line was forced through 0, then it's not allowed to go up and down and really get its right fit. So we'll show you later where that comes from, but just kind of keep an idea of that 1 is to bring in the beta 0 coefficient here. But really look at this as kind of our model matrix for linear regression. And then we look at our beta values. So for intercept, age, and tumor, you'll have your separate coefficient value. You'll see here we have our coefficients here, coefficient vector. And then we have our response, or our result, right? Our 4 patients, and what is their result. And to get this, you have, your result equals your predicted values equal to result XB. Well, also think of XB is your dot product. So in this sense, XB is your dot product. So how will we get Y if we have X and B? Well, really simple. We just do the dot product, right? So we have our X matrix, dot product, our beta vectors. That gives us our responses. And if you want to think about this mathematically, it's the same thing we did before. But do you see here the coefficients 10, 0.5, 2, -2? Those are the coefficients. And what we've done is we multiplied those coefficients by 1, 45, and 2.2, right? So you see here 1, 45, 2.1. So I'm just sorry. So that column vector is that vector is really being multiplied by the first row here. So it's just 10 times 1 plus 0.5 times 45 plus -2 times 2.1. And if you do all that, you get your Y value. And if you multiply this out yourself here, you'll get 28.3. So that's how you solve this linear system here. Now let's look at it from another direction. How do we get what if we wanted to know the beta value? Well, let's kind of work our way up on that. So let's make a new variance. And in order to do this calculation, the way we're going to do it now, it needs to be square, because it needs to be able to be inverted, because we need to create this inversion of it, this inverse matrix for it. So in order to do an inverse matrix for a calculation, it must be square. So I made a little variance here. I called it the covariance matrix, just to kind of give you a hint on that. Covariance matrix is the variance of the variable is in the diagonal, and then the variance between variables are found in the other areas too. But don't worry about that too much right now, but just want to introduce you to that topic. In this sense, for this calculation, it doesn't have to be a covariance matrix, but it's nice to have, right? So we have our matrix here. Just think of it as a matrix right now. We found the determinant. Don't worry about how you calculate the determinant too much. It's just that you want it to be non-zero. And there's just reasons for that, like you don't want duplicate rows and things. But just know if you do the determinant, which is dt, the matrix, if it's non-zero, which it is here, then we're good. It's invertible. How do we do an inverse matrix? Well, very simple. We have something called solve. Solve your matrix will give you the inverse. Okay, and here we got the inverse right here based on our solve function. And what is important about the inverse matrix? Well, the main issue is, the main thing you want to get out of inverse matrix is if you multiply a matrix by its inverse, you get the identity matrix. Okay, so here we have our matrix A times, or dot product, sorry, you need the dot product to time it. Your covariance dot product times your inverse gets your identity matrix. So if we see here our covariant matrix, dot product times our covariant matrix gives us that identity matrix, which is just simply, our ones along the middle. So we got what we want there, exactly what we would expect there. So how can we use this to solve our linear system? Well, if you remember, if we have the B equals AX, think of B as the response again, A is the covariant matrix, the design matrix, X is the coefficients. Well, in this sense, we want to find X this time, right? We already know the response in the design matrix. So how can we do this mathematically? Well, think about it here. If the identity matrix, A -1, dot product times A gives us 1, or gives us an identity matrix basically, which is basically 1 in matrix forms. If you see here, we can just multiply the identity matrix by both sides of the equation, right? So on the left, we'll do A times A -1. That'll give us 1. We're left with X, right? And on the right side, we just have A to the -1 times B, right? And we know how to solve that. Well, we just find the inverse, right? So solve covariant matrix, that gives the inverse, and then we want to dot product that times b. Well, this solve function, we could have just done this, got the answer, and then dot product by b, but the function also has a functionality where you can put a comma b, and it will find the inverse of this function and then dot product the vector on the right. So that's what we've done here. We have found the solve of our matrix from above, our b vector we have here for our coefficients, and that is given, our response, and that has given us our beta value, our x, our beta coefficients here for intercept and age, or really our variable, 1, 2, 3 here. Sorry, we're not doing linear regression right now. So we don't have the intercept there, right? So that's why you would still have a variable 1 there. Sorry about that. But it wouldn't matter either way. It would work for you. So that's how you kind of go backwards to do that. Well, how can we look at this more in the system of linear regression even farther? Okay, so let's go into our regression table, and I basically made a new matrix and a new data set here that to kind of work with, because I wanted to add a response. And so we have our cancer data, we have our response column that gives us our result, and then we have different columns, age, stage, biomarker treatment, that are our predictors, and then we have our data. And one way to kind of do this, kind of work along in the middle, is when you do your linear model equation, this happens, R does this itself, but we want to do this by hand right now. So if you just want to get this matrix, so we could have just, grabbed out the columns, right, of our predictors, but we want to have that intercept, right? So in order to do this, all we have to do is model.matrix tilde our predictors and the data, and that'll make our model matrix here for linear regression. That'll add in this intercept column with the 1s. That's basically all it does, to be honest with you. And you're left with this x as our model matrix, just like before. This is our design matrix. And we already have a response for each value, for each row in the tumor response column. We have our actual response. So now we have our y and our x, or we have our two values. So now we want to find our coefficients, right? Just like you would do with a linear model. Well, it's pretty easy. We would just really solve x comma y would give us the answer, right? Solve x comma y would give us the answer like we would have above, like we would expect. But that was only really for one. That doesn't really capture, the model in the sense that we would like to do. So in order to do that, we have to make things a little different. Beta is not going to be so simple to calculate. It's just going to be slightly different to calculate. It won't be solve x, y this time. It'll be a little bit different. And while we're doing this, we'll share a little bit more about this later, but we're trying to introduce this concept of overall least squares. And basically, I'll talk about the concept a little bit better, but we're just trying to minimize the error, basically, and fitting our linear model. In order to do this, we have to go a little bit farther and calculate beta from a little bit different formula to be able to put this in there as well too. And basically, what's happening is, I won't go into the math here, but you're dot producting the transpose of the design matrix times each side, and then solving for beta. So if you see here, we have x transpose times x, x transpose times y. So let's break down how we could do that. So remember, t is x, right? T is transpose, so t transpose is tx dot product x, right? That gives you that. T transpose dot product y, that gives you that one. Another function you could also use is cross prod. So if you use cross prod and have two values, it makes the transpose to the left and dot products by the right. Just kind of a quick way to do it if you wanted to, right? So now that we have these values, we have our x transpose x and x transpose y, then we just need to basically, what we'll basically do is multiply, once again, the inverse of the entire thing by each side, right? So we'll multiply the inverse of xtx on this side, dot product, because we're going to do it on both sides, right? So this side will turn to 1, just like before, And on this side, we'll end up with our xtx -1 times xty, right? So then that's simple enough, right? How do you do that? Well, just solve xtx, right? That gives us our inverse dot product times xty. Bam, easy. You could also do it in one form like before. Either way is fine. And then that gives us all of our beta coefficients now. It's pretty cool, right? So for each one of these values, we now have that kind of slope value that we see. So let's check this, okay? Let's do a quick linear model. So linear model is LM, response, tilde, all your predictors and your data. And when we do that, just a quick look at the coefficients of linear model, we see here, bam, they're exactly the same. Awesome, right? So we have manually, by hand, calculated the answer to a linear regression problem. I think that's pretty cool. So now we've done it the hard way, let's do it the easy way, right? So let's go back into creating a new cancer data set, a little bit more complicated one. And I've done that there. And we have a matter of kind of numerical values like age, BMI, tumor size, Ki-67, our tumor shrinkage. We have a total complete response here of 0 and 1. And then we have a bunch of other kind of integer values where we have things like stage and grade. Do we have 0 and 1 for P53 or HER2 status? Same with chemoradiation, things like that. And here's just kind of a summary of our continuous values. And here's kind of another summary ahead of our top 10 patients here. And you can kind of see what things we're going to be looking for, or how do those different predictors affect tumor shrinkage and complete response. And that's what we're kind of be going for in this workshop today. So what about exploratory data analysis? Let's jump in and kind of just take a look at the data set just to see what we got first. So first, I'm just going to do a univariate exploration. And basically, just look at the distribution of some of the continuous variables to see what we got. We see age, tumor size, Ki-67, tumor shrinkage. And we see these first three are pretty normal. It's a little bit right skewed here. But I guess that these three are pretty normal. The top right's a little bit right skewed. But what I want to get across here is the distributions of the predictors is not that important in linear models. As long as they're not extremely ridiculously off, they're okay to use. What we care about on linear models, let's just do regression, are more things like our equal variances, things like that. If we want to care about the normality, we want to care about the normality of the actual residuals, the error. We'll look at that, and that makes sense to matter. We need to make sure those look good. We care more about things like collinearity. Do you have collinear terms, or do you have unequal variance, things like that. So don't worry too much about that. Nice to see, but it's not the end of the world. Let's look at the distribution of some of our categorical variables. We see that stage 1 to 2, 3 to 4 pretty much split. We'll see our complete response, no response, is not equal. So we're going to have a problem in modeling that because it's not really equal. Our treatments are pretty equal, so those are pretty good to compare. What about bivariate relationships for our correlation? Well, let's just use the RCore package, and let's look at the continuous variables and just see their correlations and plot those. And if we do that, we see that the only significant things are it looks like Ki-67 and tumor shrinkage, and age and tumor shrinkage. Those are the only two things that are actually correlated, and they're not actually all that high. I guess Ki-67 tumor shrinkage is the highest. But it's important to know as we go farther that we have these correlations, and we take a nice little quick scatter plot of all the different comparisons, and we can quickly see the distributions again. All look normal except that tumor size one. And look at a quick, just a quick look, just a quick fitting line, really quick. Just try to see some quick differences. We see basically two here. I see age and tumor shrinkage, and especially Ki-67 and tumor shrinkage are really showing an effect here. It looks like, as overexpression goes up, shrinkage is coming down. As age goes up, shrinkage is coming down. So those seem to be the tumors are worse, or the body's not as fit, so it's affecting that. So we're already seeing some just a really quick relationships, right away here that we're going to want to look more into or hope to see a repeat of And then just really quickly comparing a couple other things, because we're going to be looking at our three things: shrinkage, response, and our basic treatments. So first, we're basically comparing our experimental standards, and they're pretty close. We're not seeing much difference, and maybe if we stratify them more to like certain other variables, we will see a difference, but that'll be interesting going forward. Where response, we didn't check the significance here, but we're seeing a pretty big difference in response and experimental, and we do have more shrinkage. So we will hope to see a model that will show that. So that's all the background. Sorry about that, long background, but I just wanted to get you guys kind of a little understanding of the underpinnings, what's behind the engine of these models and things. And even if it doesn't kind of kick in right now, it'll be lingering in the back of your head, and we move on to other topics that are more advanced, like deep learning. These are going to come back and help you out. So let's just go dive into here to what is exactly linear regression. Well, it's a statistical method, as you probably know, and it basically models this relationship between a dependent variable, the response, and one or more independent variables, and we're the ones, the predictors. And it basically fits a linear equation to this observed data. So the linear equation, you'd probably expect it to be something like y equals mx plus b, like we talked about, and that's pretty much what you get with y equals the response, the b1 sum 1x is your predictor, and then you have the epsilon as your error, and you have this b sub 0 term, which is basically the intercept of your line. And that's why you had that intercept equals 1, because you wanted to bring in a 1 times the beta 0 value to bring this into that equation. So you're kind of left with this line we're fitting where b, or a linear combination of the coefficients are kind of the slope with also a b sub 0 intercept. So we talked a little bit about least squares, and that's kind of how we help to minimize the error, but what does it actually mean? So if you think about it, I guess I'll go to first, I'll look at this here. So imagine we have a bunch of points, and we have a line that is fit these points, right? Well, the distance, the vertical distance, the observed value minus the fitted value, right? These are what we're going to define as error. And basically, if we sum all those together, each one of them, and add them all up, we're given the sum of squared errors. So obviously, we want to try to minimize that. So something least squares does, or the ordinary least squares does, is vertically try to minimize this error in response. We want the line to fit the best it can, right? So really, to do this, we're really maximizing the likelihood of, in this sense, we are minimizing the. Actually, that's later. I'm sorry, that is confusing. That's logistic. What am I talking about? I'm getting ahead of myself. We just want to minimize this error, basically. That's all we're trying to do. It's pretty simple. The less error you have, the more closely the line will be along its dill. So let's try to geometrically look at this. So if we you can imagine the left here, we fit our line here to minimize all these perpendicular distances, and then we have basically an error, a vertical error for each one. Well, the vertical error is our residual value. And basically what this is trying to do is, so if our residuals we want them to be uncorrelated, we want them to sum to 0 because the line is equally below, there should be an equal number of error above and below the line, right? So the residuals will sum to 0, and they're uncorrelated with the predictors. So you won't see, all of them clustered to one space or not. And also you want your residuals to be orthogonal to your fitted values. So your error should be orthogonal to your figured values. Orthogonal, remember the A, B cosine theta, the dot product, right? So the dot product is baked into this equation here where we solve kind of that fancy beta equation. It's baked in there basically to only find values that maximize this perpendicular aspect, right? So it basically fits that function to where all the residuals basically have to be 90 degrees away from a horizontal baseline, right? And that helps to minimize that that error. So you're going to want to see if you basically take your fitted value, like you see right here, it's your fitted value dot product to your residual value. Each one is your dot product, and that is equal to 0. So that's just showing the dot product of fitted values is 0. So that's what we'd expect. So that's kind of the general math, pulling from that linear algebra back to how that formula is executed. So let's take a quick example, a univariate example of one predictor. So we have just the LM to run linear model, the response, and then we have our predictor, and we have our data, of course. And let's just look at the results here and see what we got for one predictor alone, so nothing else is affecting it. First, we see residuals. The median is close to 0, so it's kind of that do they sum to 0 deal, so that should be kind of look the same above and below. Your estimate, that's kind of that mean, that slope. So we're basically showing for every increase in unit of age, we're seeing a negative 0.2 decrease in our actual response. And so it's pretty easy to see. It's just a slope when you have one value. Univariate is easy to understand. Your standard error, your t-value. Most importantly, you have your probability, if it's significant or not. Here it is significant. We have our residual standard error, sometimes called RMSE, 13.36. It's just your average area among the entire line. We have our multiple R squared value. R squared different than sum of squares. It's just a measure of the variance explained, and the higher the value, the better. Adjusted, it's more when you have multiple variables, it'll adjust for you better. So this is saying that 29% of the variance is explained here, and we have a low p-value here. And once again, we just kind of put it into a table here. We're kind of seeing what we just talked about, and we take a glimpse at this model. You can take actually a glance. Remember, a glimpse is the tidy for looking at matrix structure. A glance is the type is what you can look for to grab in some of your simple model performance. And we're just seeing, once again the R squared value in our RMSE, which is pretty decent for this. And now we're just going to throw this in a plot, visualize it, and we're seeing that kind of negative 0.2 slope along the line for just our age versus tumor shrinkage. So as age gets higher, the tumor is not responding as well, which kind of makes sense because an older patient would have a harder time fighting off the cancer. So let's just make a full model now. Let's just add in more of our variables. So now we have a bunch of variables added in here. It's a kind of a multi-model regression here. Once again, we see our residuals are pretty much in the middle, and now we have a lot of different estimates. So remember, it was easy when there was one, right? It was just the slope. These are still the slope, but it's a linear combination of these values to make that slope. So it's just a bunch of kind of slopes that are basically have an additive effect in a sense. But what jumps out to me really quick is the really high ones, the stage, -5, and the chemo radiation. These are all very high values here that seem to have both a negative and positive effect. And they also are both significant. So we're kind of focus on our significant values. We'll come down here, we'll be able to see those here, and we see our coefficients. And we feel, pretty good about those things. We're age, stage, the Ki-67, more overexpression, we have lower shrinkage, and we have more treatment, we have higher shrinkage, right? So let's just plot those. Basically, I'm just going to plot all those regression coefficients, the same deal with their 95% confidence interval, and red if they are significant here. And we see, once again, we're seeing this really negative effect with stage, really positive effect with the chemo and the radiation. So now that we have our model, let's just kind of check some of the assumptions. If you just plot the actual full model, the base R gives you these kind of values. The top right's our normal plot, we know that. On the left, the two plots have to do with equal variance, so you want to kind of distributive values with the line being relatively straight. The residuals versus leverage, looking at your Cook's distance, which is a measure of outliers. And you kind of look on the right here, we have some outliers here that are kind of pulling the line down. It's not horrible, so we're not going to worry about it too much, but something to be aware of. these points that maybe need to looked at. Let's make this we'll tidy it up. Let's throw all these plots into some tidy plots. And I guess one thing here to show you, this Cook's dot distance on the model is how you actually calculate the Cook's distance. So just keep that into everything else is just normal plotting. You guys should already know. And this is just kind of a prettier way of doing this, where we have our QQ plot. Once again, our residuals here. We have our Cook's distance, where we see a few points above we're not worried about. And I think this is a really good plot. This distribution of residuals, which we talked about earlier, is the important one to actually be normal. We can do the Shapiro test just to make sure it looks normal. There's another test called the Berish-Pagan test. This is for the equal variance. You can run that using the CAR package, and that actually shows we're good there too. And then also the multicollinearity CAR package again, this VIF. This is all just on the full model, and this gives us our idea. As long as we're below 5, we're good on that. Looks good. So the model overall looks pretty solid, that full model. And remember, this is not the best model. We didn't worry about going and trying to find the best model here because I didn't want to overload you with stuff. We could have looked at the AIC values. We could have done a step through, which I'll show you later. So we're just kind of showing you how to do it. At this sense, we didn't choose, the best model and this step, but you will see that happening in the additional assignment. All right, so we're halfway through the two methods. Let's step in and look at what is logistic regression. So linear model was when we had a bunch of points, we had a response, we had our predictors, and we had basically a line we wanted to fit. And there's a continuous results, right? Logistic regression is completely different. This is a model that's used to model the relationships between, independent variables, our predictors, but now a binary dependent variable. It's not continuous variable anymore. It's 0 or 1. They're trying to basically classify into two different groups, right? So basically, it's predicting the probability that an observation belongs in the 0 and 1 class. Now, it's not giving a 0 and 1 answer. It's giving a probability, 0.42, 0.1, whatever, right? And then we'll set a cutoff, split into the two classes, and your final result will actually be that 0 to 1. Now, I won't go into the math behind logistic regression and the logit function because it's kind of complicated. I don't want to overwhelm you guys today since we already went through so much linear model stuff, but we might talk about it later when we talk more about machine learning. But one really quick thing I can show you is if you look at a sigmoidal function is 0 swipes up to 1. So it just slopes up like this, right? It's a 0 here, so it's symmetrical. That's a sigmoidal function. Sigmoidal function is anything with 1 over 1 plus e to the negative x. So I think one thing to look at here, what they've done is they've taken logistic regression. The mathematicians, those suckers. And we've just forced that into the sigmoidal function. So we're doing the same. We're looking for the same kind of thing, but we're putting it into the sigmoidal function to be able to force it into those different classifications. And we've solved basically here to a more fancy version. And this is what we'll be actually using to solve for our beta coefficients. And another way of looking at this is you're solving using kind of the logit function in a way which is similar to sigmoidal, to solve the linear, the natural log of P over P1, which is kind of a probability-like thing. And it's basically just saying that you're going to have you're basically getting a probability that's going to be forced categorically. So that's kind of the background on that. I can say so what's happening is your coefficient is basically giving an effect on the log odds, basically, in a way. But it's a little bit different to look at because it's not, before we had the response variable, so the estimate was directly affecting the y-axis. Now we're affecting probabilities, so it's more the log odds. And we'll show you how to calculate that later. And here, instead of minimizing the sum of squares error, we're actually using the loss function, which is an extremely important function in machine learning and deep learning. And it's basically, there's all different kinds of them, but they're the fundamental way to look at error. And once again, I won't go into this one too complicated. We'll talk more about it later, but basically it's minimizing the negative likelihood, or another way of saying it is you're maximizing the likelihood of each probability. So it's really a statistical measure, and we'll kind of go into that at a later point because it's pretty complicated. And basically what you're getting is the results are being forced into a 0 and 1 category. So you could have a value of 0.2 here. It would have been cut off down to here. Maybe. Here we have the cutoff of 0.5. It could be different places. And that your final results are going to be 0 and 1. And for that. And you're going to get a loss function. Anything below like, I guess like 0.4 or so, 0.5 is and lower are pretty decent. 0.7 means it's 50-50. So let's work on a couple simple examples. So let's do just a very simple one predictor once again. So the way you do this is you use GLM instead of LM, and you say family binomial. You don't have to put link equals logit, but it just being a little more specific because there's other models. You can also run linear models inside this GLM too. We'll talk about that later. But really just do GLM, your response variable, your predictor, your data, and family equals binomial, and that'll get you your model. You look at the summary of that model. A little bit different. There's no residuals anymore, right? We have this estimate of stage. It's negative 0.58, so we know there's a negative relationship, and we have our p-value, standard error, and so we know there's a negative relationship. We don't necessarily know what this number necessarily means yet. But look at the null deviance. That's what the model would be if you did not add a predictor. So whenever you add a predictor, you want to see if it's better, which it is better, it's lower, and we see an AIC, decent value, but the AICs are hard to kind of look at by themselves. It's more of a comparable value when you compare different models. And so one way to kind of understand, I think the best way to understand, or easiest way to understand these estimates is just to form an odds ratio of it. So in order to get the odds ratio from this estimate, it's really simple. You just do Euler's number, e to the negative 0.5807, just e to the whatever, right? That gives you your actual log ratio. And then now there's a 0.56, so for each change in stage, there's a 0.56 factor of change on that. And what you can do is you can just do 1 minus 0.56, that gives you 0.44, and you multiply that by 100, that gives you 44%. So basically, whenever an odds ratio is below 1, you do 1 minus odds ratio. Whenever an odds ratio is above 1, you do odds ratio minus 1, and then you multiply by 100. So 0.56 is under 1, right? So 1 minus that gives us 0.44 times 100 gives us our 44%. And that's basically just saying for each unit increase in stage, we're getting a 45% decrease in odds of that actually happening, of that being true, right? So how can we visualize this? In stage 1, we're seeing this probability of, this first probability of response. Probability of response is the probability of it being 1. And then we're basically just seeing it as time goes on, it's going down, right? So the probability is going down 44% pretty much each time we're going through that and getting lower. Okay, so that's a univariate logistic regression. What if we do more, take more values? Well, I've taken more values here. I left out radiation just for fun, just so we can see if chemo affects things different. But we've taken just, because we're kind of playing around today, right? So you can just take what you want, make a multivariate logistic regression, and get the summary. And we're seeing our null deviance is even better, our AIC is even better, so the model seems to be working better. And we look at all our estimates. We only have 3 actually that are significant. Our stage, which is negative, we already knew that, right? We've added a couple more now. Chemotherapy and treatment are 2 interesting new ones. So let's look at the odds ratios once again. And we see, stage is the same, but we see chemo has jumped up. It's pretty high, 2.26. So 2.26 minus 1 is 1.26. 2.216 minus 1, because it's above, right, gives you 1.216, right? Which would give you 121%. So every change, so doing chemotherapy would be 120% chance higher odds, right? Where treatment of standard would be 1 minus, so you're looking at what, 61% negative if you have the standard treatment over expression. Because remember, you're doing, basically once you calculate that, you look at positive or negative in the estimate to see, which direction you're going. So this all makes sense. What's interesting is showing the experimental treatment's a little bit better, which earlier we saw it was a little bit better in the tumor shrinkage. So as far as fitting this model into predictions, these are what we're seeing. And if we just do kind of a forest plot on those to see what's up, we can look at the different odds here, and we see that the three significant ones are showing the different odds ratios of their effect on the model. So now that we have our model, the cool part is let's actually predict what we would have predicted on the data if we had the data brand new, right? So what we're going to do here is predict, and I'll say now is this is not the way you really do it. You would do cross-validations, leave out part of the data. There's more complicated ways of doing this, but I just don't want to get into that today because we want to build upon that once we get into machine learning. So this is just a very, very naive way of looking at that. Think about that. But it's your first step moving that direction to understand these ways of validating models. So I still think it's useful. So we're basically, what we're doing, we're taking our full model and we're doing a predictions. So based on our model, what would the prediction be, 0, 1? Or what's the predicted probability for each of our patients, kind of looking back at them, right? But since we trained the model on this data, that's what I'm saying, it's not the best way to get the response back, but that's why you would leave out data normally in validation. But don't worry about that right now. We're just really looking at the very beginning nature of these concepts. So just think about we're just going to predict the values based on our model. So now we have our real model, we have the real results and our predicted values, right? And we're going to make an ROC curve, and that basically compares the sensitivity and the specificity of the model and shows it to us. To do that, we just do ROC and then the two different response vectors or columns. So we get our rock object here. We can plot that on here and just take a look at it. And we have an AUC, which is the area under this curve, basically. And you want a higher area under the curve. The more this line is up and close to its to its axis on the top, and you have it would give you a higher area under the curve, you have a better model performance. Anything over 0.7 is pretty solid. Anything over 0.8 is darn solid. So we're doing pretty good here. So what is sensitivity and specificity? So that's a good question, right? So I guess first, another thing you do is you can set things like Uden here. What I did here is I'm basically calculating a threshold. What is the actual threshold? It's not going to be 0.5, remember? What's that threshold to classify into 0 or 1? And we're using the Uden method here, actually. So basically, I'm choosing my coordinates, my best coordinates. So I do rock object best, and then best method Uden, and that basically gives me my threshold and my sensitivity and specificity for this actual model here that we're showing. So it's not doing anything new so much. It is just looking at the model, and then when it does the classifications, then it does use that threshold. But let's look at the performance in general. So AUC 0.723, my threshold 0.24, my sensitivity, once again, remember the coordinates, rock best. I can use that to find my sensitivity and specificity. Sensitivity is our positive rate. So it's kind of a rate of how often and how well we're finding our true positives, right? And or really just think of it as positives in general. How good are we finding our positives, right? And the negative is, what's our negative rate? What's our rate of finding the negatives? And how does this balance out based on what the values really are? And that's how you're getting this kind of balance. Obviously you want a higher, you want a high one for both, right? So I mean, the perfect would be 1, 1, right? So you want them both to be high because it's your ability to find those values in the matrix, in the result. And what you can do, take one more step farther, and basically you can look at those predicted actuals and make a actually. So what's happening here is I'm basically calculating the actual predictions based. So far we've done the probabilities, right? So now I'm taking those predicted probabilities and I'm just saying, are you over the threshold? If you're over the threshold, you're 1. If you're not, you're 0, right? So I'm creating, instead of comparing the, for the ROC model, instead of comparing the predicted probabilities, now I can have the real response, right? So now when I can do response against class, which actually is the actual class of predictions. So now we can actually make a confusion matrix, which is just, you can just table predicted versus actual, and it can kind of give you this here, and this is extremely important. I'll show you how to do this better later on and much prettier with tidyverse, but I just want to kind of introduce you to this right now. And what we see here is the actual values, 0 and 1, and the predicted values for 0 and 1. So for this point right here in the matrix, the actual is 0, predicted is 0. So that means it's true. It's a true positive value, a true negative value. And here we have actual 1, predicted 1, so it's a true positive. So true negatives I have found, true positives I found. And then here we have a false positive. I mean, look here. So, a false negative here, right? It should be 1, but it's 0. It's predicted as 0. It should be over here. So that's a false negative. It's not a negative. And here too, here's a false positive. It's actual 0, but it's being put in the 1 column. So that's a false negative, false positive, and your actuals. And if we kind of do a little calculations here, we can you can kind of look later here, but you're basically, per example, you want the diagonal, right? So you want these two values divided by, so you're basically summing these values divided by all of them. That gives you the accuracy. And then you're kind of just finding your different values and looking at, dividing by what they should be. You can kind of take a look at this later here because of time, but what you're basically getting is, and when I show you the function, this will all be done for you. You don't need to know how to do it by hand, so don't worry too much about that. Just think about what we're actually, the theory of what we're talking about. So our accuracy is just, it's like our true positive plus our true negative divided by everything else. True positive, true negative, false negative. It's just kind of a general accuracy, a general measure of just how well the model is performing overall. It's overall accuracy in every aspect. Our recall is exactly the same as our sensitivity. It's a measure of the positive rate. How well are we finding positives in general? Precision is a measure of how well, what's the precision of those values we're finding. So we're doing well in recall, but are they actually really positive? So if we found 100 positives and only 80 were actually positive, then our precision will be 80%, for example. So that's really important. So we kind of look through that, and our F1 score is a measure kind of all that. So our precision is not too great here. Our model looks good, but our precisions aren't too great. So you can see the discrimination is not too great here. It's almost, it's 30-60. It should be a lot closer. That's why we're not discriminating. We're not doing a really good job of discriminating those values. We're doing a better job of discriminating the actual 0 value, the non, the negative values and the positive values. That's why that precision is kind of bad there. So that's a good example of your accuracy can be good, but your precision is not so great. So these important things to think about. One thing you can do, also a calibration plot. Don't worry too much with the code. You could just copy that code, and it's just putting in the predicted probabilities basically, and you have your response, just pulling everything from that cancer study data set basically, and you get this calibration, and basically on the bottom you have this mean predicted probability, the top a mean observed probability. So if we're skewed on the bottom, we're over predicting. If we're skewed on the top, we're under predicting. So just a good last plot to kind of look at how you're doing on that too. All right, so now we've gone through the crux of everything here, and I just wanted to go over a couple more just simple advanced topics and applications you can do, just adding on things you could do with this data, because I didn't want to overwhelm you before. So the first thing I want to look at is the interaction terms. If you remember last week when we were doing survival analysis, we could do interaction terms as well when we were doing our making our model. So you see here, instead of a plus, we have a times here. So whenever you have a times between two predictor variables, then you're looking at the interaction of this. So if we do a simple linear model, we look at the actual result, we will see here that we actually have this interaction term, treatment chemotherapy, with its own estimate. Here we see it's non-significant. So we're basically seeing this interaction between chemo and the standard treatment seems to be non-significant. And you can think of this in terms of, is the chemotherapy working in standard versus experimental? So it doesn't seem to matter if it's in standard, whether the other ones are kind of showing up the way we would expect. Stage is down, chemo is up. And if you kind of look at think about this just generally in the plots, we can kind of see that here that chemo is working for either of them, right? We're not really seeing an advantage to it in the standard treatment. I think that's what we can see here with the interaction. So there is some interaction between those things, but it's not necessarily. So if we took it at face value, it would say that using standard chemo works better for tumor shrinkage. But I don't really see that. Maybe a little. We'd have to really do the t-test here to understand. But I think what we're really saying here is the treatment is the chemo is what's important, not what treatment you are actually under. So that's how you can look at the interactions. And if you just looked at the models and compared the ANOVA of the two models, like we did that on the ANOVA day, if you do ANOVA between two different models, and I basically just made a new linear model without the interaction term, and I just basically took the two models, and because we have our interaction model, so model 1, no interaction, model 2, interaction, ANOVA. Is it better? No. 0.45, it's not better. So we're not gaining anything by adding the interaction term. So now let's look at polynomials. So what is a polynomial? Polynomial is like x squared, x cubed, x to the fourth. So basically you can add a polynomial term to try to make the model a little bit better. Here we added age with a 2. So poly age, comma 2 is adding an x squared. So we're fitting age to an x squared, basically. We could do that with any of the other ones too, and just add polynomials to try to fit the data a little bit better. Let's compare this to just the normal linear model. So just exactly the same, just one as a poly. And let's compare these two models here. And we see that if we do an ANOVA between the two of them, it is not helping, once again, to add the polynomial. And just the way to think about what the fit would be, a polynomial fit would be more of a curved fit of the data. That's what you would expect. If you had an x3, you'd expect more of the x3, value, the way that polynomial actually looks in real life. So that's how you would fit those. Sometimes those fit a little bit better. I think this is another really important advanced topic. Well, this is what I mentioned earlier, where we weren't looking for the best model, we were just trying to introduce the topic. Here's how we could actually look for the best model. And we used this step function back before with our survival analysis, or our Cox hazard. Let's see how we could actually apply it here. So what's cool about this step function is if you have a model, and you can do direction forward, backwards. So if you had a model, if you do the full model, and you say direction equals backwards, it basically uses the entire model and then calculates everything for it. Then it takes away one of the predictors, recalculates everything. It does that for each of the predictors respectively. And if the model gets better with the predictor out, it takes it out. And it just keeps going down through until you have one left. And then it basically gives you the best model based on that trace. And trace equals 0, it just means it's not going to talk about it. The more numbers, the higher you go on trace, the 1, 2, it tells you more what it's doing, gives you the AICs, all those values below. We don't want that information. We want just the final model. So if you put in forward, you'd have to put like tumor shrinkage equals age and then tell it all the rest of the other ones for it to go forward. It's a little more complicated, but you could do it that way. Same with both ways. If you put both in, you'd have to tell it which way to go both ways, or it wouldn't know, right? So full model already tells it all the information, so I think that makes it a little bit better. But you can play around with that, go either way, move around, see how that actually affects your model in general. And when we do that, we see that KI67, let's see, age, stage, sex. So sex, looks to me like sex and tumor size have been taken out, right? So we have 1, 2, 3, 4, 5, 1, 2, 3, 4, 5. So we still have, we lost sex, we lost tumor size, we lost treatment too. So we've cut off some of the fat, and let's look at the results. Residuals look good. Now everything's significant, of course, because it found the best model, and it gives a pretty low standard error. So it's we could argue that is one of the better models for fitting the data, and it kind of makes sense because we knew stage matters so much, and we knew chemo and radiation matched so much, we can actually compare those models. We have our full model we already know, and our step model, the one that we step down, right? And we kind of see here, look at some of the variables. Really, everything looks very similar, to be honest with you. AIC and BIC is a little bit better. However, the RMC is a little bit higher. So you go either way with this. A lot of these times, maybe the simplest model is the best because you can interpret the variables better. But anyway, that's how you step down and step through and calculate. Use that to get the best model. And you can go deep in there and find all those values for each model and see what the comparisons were. All right, so let's just go through a few practice exercises to kind of read, just to kind of knock home some repetition of what we've gone over. I'm just going to make a new data set here to do some matrix operations, just some patients and genes once again. Just a kind of reminder, if you want to calculate the mean of a column, it's column means. That would give us the gene expression per patient, for example. Kind of a new concept, center the data. We'll be using that later. You could use sweep the matrix and two genes means. Basically, it's just subtracting. It's just subtracting the means basically. So gene means, subtracting, and it's just leaving two values. But there's actually, I think I can give you a better tidy version of center. Well, but you can use this to center the data. But I think what is important is just to understand the concept of centering, and it's basically taking the mean of an entire column and subtracting from each of the variables. And that gives you a mean of 0 and a set standard deviation. And this allows you to compare things later on. It makes it more interpretable for later models, especially deep learning models. If you wanted to get the z-score, you would divide the center. You would center the matrix and then divide by the standard deviation. That gives you the z-score. So this is all just standardizing all the elements to be more interpretable for models, and it's debatable whether you use them for a model or not. It all depends on the situation. But later on, especially for deep learning, you're going to want to do it almost always because the model interprets it better. But just a really quick early look at centering the data and what that actually means. And then the covariance matrix we talked about a little bit earlier. If I want to calculate a covariance matrix, I put in my matrix and just do COV. And that gives me my covariant. And you can see gene A has a variance of 1.9, while gene C has a variance of 8.3. Likewise, AB is negative 1.2, blah, blah. So that gives you all the variances for the matrix. And one thing you can do with that is find the eigenvalues. That's something we'll do a lot the next lesson probably, but we'll talk more about it. But the eigenvalues can be found by eigen in your covariance matrix, and it just grabs, it finds those values. There's your 3 values. You have 1 for each predictor. And then one cool thing you can do is you can just sum these values up and divide by each of the things, and you get your principal components of PCA. So if you just find your covariance matrix, find your eigenvalues, add them all up, and then divide the first number by the sum, you get your first principal component for PCA by hand. So that's pretty cool. So I showed you how to make a linear model coefficient by hand and do a principal component by hand. So I think that's really cool in my mind, and kind of get a good understanding of what's going on just under the hood of some of this math, some of these, I guess some of these packages. And then let's just do a quick solve of linear systems, just like above. Let's basically make a new model matrix. So basically just making a new matrix here, the model matrix, right? And I have true, so I have my y, I have my response, and I have my beta. Well then, if I have my y and beta, then how do I find, if I have my model matrix, right, and my beta, how do I find my response? So this is the model matrix, sorry, this is the model matrix, this is the coefficients. Dot producting those together will give us our answer, right? So here we go. X design, dot product, beta true. We're just dot producting them both together to get our response. And we added a little noise in here too to get a little better value if you'd like, because it's more of the fit you would see, because that's what you would have in real life. And that kind of gives us our beta predictor values. I mean, I'm sorry, I keep saying the wrong thing, response. We're getting the outcome, the response. So we have our design matrix, we have our coefficients, we dot product them, and that basically is filling this equation with the error. That gives us our outcome for our patients. Now, if we want to go the opposite way, we'd have to start out with, remember, we would do our transpose X design dot product X design, transpose X design dot product to Y, right? And really, the really quick way of showing it would be just to solve that one and that one. So we basically, and we can use cross product for that too. Really, the easiest way to do this would be solve cross product XTX, cross product XTY, but whatever. So we're just solving that equation like before, transpose dot product X, transpose X dot product Y. We get our two variables, then we find we use solve to first do inverse of XTX times dot product XTY. And remember, if we actually have our response and we have our design, we can get our beta coefficients here, which we've gotten back by estimating the beta from this. So now we've gone, once again, both ways on that equation. And then we're just doing a really simple linear model, basically on exactly what we did, just to check that. And we see here that they are the same. So our calculations are actually the same. And we kind of compared the true and the estimates based on that noise to show they were really close. A couple more linear regression things. Let's do a quick linear regression again. So what I did on these two practices, I basically just gave you the same thing. Just recreate the same thing we've done on your own. And then do one more little tiny thing. Where here we'll apply a prediction. We'll make a prediction model and we'll apply it to guess some outcomes based on new patient data. So that's kind of cool. So let's do a simple model here, stage only. And see what we got here, a big -6, we expect that, right? Let's add a clinical variables. So down we'll add age and tumor size to our model. We have a clinical example, and now we'll kind of show what we've done there. And let's make a treatment model. We'll add treatment, chemoradiation, just added a few more variables, just kind of building the model, adding complexity to it. And we get our result here. We see chemoradiation really high, stage low. Those are our biggest effectors we've seen the whole way. And let's compare these three models using the R-squared values and RMSE. And we'll see here that full treatment has the highest R-squared. It explains 32% of the variance and has the lowest R-squared. It's really the full model. With this model, in the comparison of these models specifically, the full model is the best. Now you can see how there could be all sorts of different combinations of models that you could possibly have. And depending on your data and the situation, you might want to use certain ones or the others, or you might want to care about the overall best model. It just matters what your actual data is showing. And then we can check for collinearity really quick, things like that. We show that's fine. We check the residuals. Once again, they look pretty good. What's cool here is what I want to show you is let's do a prediction for the model. Now we fit the model in the data. And that's fun, that's great. We saw some relationships, but now I want to predict something from this model, which is to me the coolest part. So let's use predict here. We basically just made new patients. They have, stage, age, tumor size, the same things they have. And basically we're going to do predict, use our treatment full model, and we'll put in the new patients and predict to a level of accuracy of 0.95, right? And we do our predictions, and we look at our predictions, and we see here in the fit, we see a tumor shrinkage of 52.4 here, and we see 22.3 here. So we see a much higher, so for a lower age patient on experimental treatment and full radiation and chemo, we're seeing a really, really, really good tumor fit, right? And we're also seeing a low stage. So these represent like all the things we've seen the best to be, right? We've seen stage be the lower stage to be great. We've seen experimental to be slightly better. We've seen chemo radiation to be a lot better. So it doesn't surprise me when we see a higher stage older person on standard treatment with a higher tumor and no chemo radiation that they're going to have less tumor shrinkage. So that matter. Model predictions are mattering. That's good. You want to see your model to matter, right? So we're showing that we can make reasonable predictions from new data now, which I think is really, really cool. That's one thing I want to really you guys to function on it, to focus on, is building predictive models for all of your projects, because that's just the most important part of the whole project, is to be able to predict on future data, to be honest, in my opinion. Okay, so finally, let's do one more logistic regression and create some risk groups at the end based on our predictions. So what we're basically going to stratify by stage, and we're seeing it's a pretty good distribution except in the highs of our responses. And let's build a univariate model for each one of them and kind of look at the results of those from the odds ratio. And just looking at each one specifically by itself, we see pretty good. If you look at the ones that are actually significant, the top three, we are seeing that, chemo is definitely in stage are showing the most effect, which we've seen before. So it's not too crazy. And then, but when you put things together, interactions happen. So even if you don't have the interaction term, interactions still happen overall in the model, just not between terms, right? So the more complex the model, the more interaction is happening, right? And even if some things don't work really well, when you put them together, they work well. You just never know how the effect's going to be. But anyway, let's make this multivariate model based on these 4 predictors, just like above. We get our results, and they're kind of expected. High chemo once again, high stage once again, and treatment towards standard is kind of a little bit negative. Once again, things we expect, we saw before, and this is our model. But what I want to do is let's calculate our predicted values based on our model, right? And do our ROC model, get a pretty good AUC. I'm basically just doing exactly like above. I'm not changing anything. And what I want to do at the end is create a risk group, which is kind of cool, I think. So I hope you guys can go over this again to get some repetition, and then create a risk group. So when look at the predicted responses. So based on our model, we're making more predictions, right? This is not on new data. It would have been, I should have put new data in, but it would have been cooler. But let's just look back at our data because we want to do the risk groups, right? So we're looking at our predictions, and we're just separating this out into different values. And if we do that, we basically stratify our risk into 3 different groups here. And as you'd expect, and we look at our predicted probabilities to be in those groups, and our actual rates here, and our actual complete responses. And let's kind of visualize those. First, we see our AUC model, AUC in the curve, 0.721, pretty good, pretty solid. And then let's look at the groups that we stratified into, low, medium, high. We're seeing what we would expect under the response, and we're seeing, based on our predictions on our fitted model, we're seeing good stratification between the different response and the groups, which shows that it's likely a pretty good model. So what I want you to get out of that is some repetition and the idea that you can make these predictions from the model and make new risk groups or more risk scores, things like that. So just a summary of the week. We went over some basic matrix algebra that was kind of fundamentally behind linear regression. We went over kind of basically how regression start to finish, as well as logistic regression as well. Talked about building models and interpreting them and doing predictions and different visualizations and everything. And here are just a quick reference guide for some models and interpretations just to help you out. And I made an additional assignment. This one is really building off what we did. So it's using the same data sets, the same values, and just adding more things, more complexity, more things to them, more corrections, more things you could do with them. So if you want to take a stab at them, that would be great. Try some things out, work on them, and try to get a basic analysis for each one, the best you can. And you can take some kind of guide from what I've showed here in the summaries, and then take it a little farther and look and see a few of the things I've done that we didn't necessarily cover because I didn't want to overwhelm you, but get a taste of what's possible to really project these models a little bit farther into advanced way of using them and to get a little bit more out of them. And I think going through this, all the answers and solutions are there. So please, if you have time, take a chance to go through those, see, get a taste of some different things that we haven't had a chance to cover. And it just very, very comprehensively goes over a couple of models for linear and logistic regression. And finally, here's some different additional resources you can go to check out that might help you out understanding some of these things. And that's it. Great job, everybody. I'm really excited that we've gone through 5 different sessions in this workshop. And, I feel like you guys have done a great job of mastering things from descriptive statistics to basic t-tests, multiple comparisons with ANOVA, survival analysis, and now linear and logistic regression. I hope this has given you a comprehensive statistics toolkit to be able to move forward and do some more cancer research analytics. And I guess check out the digital assignment and research to have a chance, and stay tuned, in the future for some more workshops on some more advanced topics. And with that, I will see you guys later.